7, 9. So for this kind of number, we know the starting point is 3, but we don't know the ending point. It also same like this as this kind of number. We don't know the starting point and we know the ending point. These two list of this number we call infinite number. Point. Another situation, we don't know the starting point, but we know the ending point, and it also, if we don't know the starting point, then we have some partial of number, but we also don't know the ending point. All this kind of number we call infinite number, but it put in sequential. For example, 3, 5, 7, 9. Or maybe we can also have 9, 7, 5, 3. This is in descending order. This one is ascending order. Today we will talk about the type of this list. It means we talk about the sequential of number. Okay. What is sequential? Sequential is list of objects. Okay, list of objects, but for our case, actually we focus on list of number, where we arrange in a defined order. We start with first element, second element, third element, and so on. So this list of object, so list may be stopped after n step. So we can put as n element in set n, or it may be go on forever. So that's why we call finite. So the element may be different, on some may be repeated, like this one. 1 0 0 1 0 1 0 0 1 1 1. But the number that we are only consider on this dot means and so on. See, this is the discrete definition, and so on. Only 3, not more than 3 or less than 3. Where it refer to and so on, like this one. Okay, this we call infinite sequential because here we don't know the ending point. Okay, another example. Given to you 1, 4, 9, 60 and 25. Okay, before that, once we refer to example 2, once we look on these sequentials, we can see the pattern. First, this pattern in in ascending order. Once we start with 3, 8, 30, 80, and 23. But between this number, from here to here, here to here, we know because of this is ascending order, we say plus what? From here to here, plus 5. From here to here, plus 5. And so on, also plus 5. This is the pattern for this kind of sequential. But for example 3, we can see the pattern, but we don't know how this pattern created. For example here, 1, 4, 9, 60, 25, and so on. Then, what is the pattern of the sequential? If we put like this one, here is this ascending order. Can we put like this one? From here to here plus 3, from here to here plus 5. But this is not the exactly pattern. The pattern ascending, but not in a fixed order. Here 9 to 16 plus 7. So how we know this kind of pattern? And the second idea is, what is the next value here? So they have another type of pattern we call based on the number itself. Once we look on the number, previously we look between these two number or these two number, but for this case we look on the location of each of the number. For example, here, number 1 actually at the N1, here N2, here N3, and so on. So once we look on the location of this number, we can predict the pattern while we look on this location. Okay, what is the relationship between this value, means with its location, this value and its location, this value and its location. So once we look on each of the number, we can see the pattern where the value is the location value we put square. So once we put N1, this one power of 2 or 1 square, the value that we can get is 1. Here 2 square 4, 3 square 9, 4 square 16. So we can predict the next value here, where this location is N6. So we, based on this kind of pattern, we can say that 6 square, the answer will be 32. So we can say that the pattern of this kind of sequential is positive number square. And what is the next value? The next value is 36 and 7 square, 8 square, we can get 49, 60, 64, and so on. So based on example 2 and example 3, there are two types of sequential. First, based on the terms, we call this term. This term, what is the relationship between this term and the previous term and the next term? This the first pattern of the sequential. The second pattern is based on the location of the term itself. So based on these two ideas, example which is example 2 and which are example 2 and example 3, we can generalize that there are two kinds of formula which commonly used to describe sequential. First, we call recursive. The second, we call explicit. So the first, recursive formula. So the recursive formula actually we refer to the previous term to define the next term. Every recursive formula must include a starting place. It means when we talk about recursive formula, we will look on the previous term in order to find the next term. It means here we have N1. We must know what is N0, and based on the N0, we can predict N2. For example, here, given to you 8 and given to you the starting point. See, the starting point 3. So we can know and we can predict the next term. 3, here 8, the starting point 3. So we know the range between here is 5. So for sure, from 8 to the next term, which is plus 5, it will be 13. So this kind of formula we call a recursive formula. But they need two things, at least in order to talk about a recursive formula. First, we must know the next, the previous term in order to predict the next term. The second thing, we must know the starting point. That's a recursive formula. Explicit formula, we refer to the position of the element. It means position of the element. For example, we know at N0, what is the value? At N1, what is the value? Then that value for N1 must have relationship with this location, means location number 0, N0, N1, and so on. For example, previously, first the location for N1, 1. The location for N2, 4. The location of N3, 9. So the relationship between this value at this location, so what is the relationship? Based on this pattern, we can see that each of the location we need to square. Means n square here. Means all this value we need to put n square in order to get the number at each of the value. Okay, so it refers to the position of the element in the sequential. For example, an element will be referred to as an. So all this n1, n2 we refer as an. So we will utilize later an. An means refer the whole sequential n1, n2, n3 and so on. So we generalize it. That sequential represented by an. Okay. Now we move to specifying on a recursive formula. Okay, again, we use the same example, means we refer to example 2. Given to you 3, 8, 30, 18 and 23. See, once we look on the first element, the starting point is 3. So because this sequential we represent is an, so once we refer to the first value, so we put a1 because the first location. So a1 equal to 3. So a2 equal to 8. So because of the pattern is fixed in the ascending order, fixed value plus 5 plus 5. So a1 plus 5 will be 8, where 8 is at location a2 here. So in order, based on this pattern, how we predict the location a here? A6 means 1, 2, 3, 4, 5, 6. So a6. So a6 will be based on a5 here, a5 plus 5 here, plus 5. So the value at a5 plus 5 will be 28. So this is the pattern of the sequential, means this based on this is the sequential. Based on this sequential, we can get the pattern. So this pattern we formalize it as an. Refer to a1, a2 and so on. So an equal to an minus 1, because here an, here a2, a1 and a2. So here actually an minus 1 will be a1. Here, for example, a2 minus 1 will be a1. That's why I put here an equal to an minus 1. This value fixed. So plus 5. This is the formula in order to represent this sequential. So today's topic we will talk about two types of formula. First recursive, second explicit. Based on the sequential, we can produce a formula. For this case, we produce a formula, recursive formula for example 2. Okay, so then we get an equal to an minus 1 plus 5. So each of the formula must have a range. It's only valid for in a range. So we need to justify the range for this value, for this sequential, sorry. So in recursive formula, we say an equal to an minus 1 plus 5 for, in order to represent the value, we put for 2. How we get this value is 2. 2 actually involve, how many variables involved in this 2? Less than and equal and less than infinity. Okay. How we get this kind of range? 2 represent 2 variables involved. Here, less than and less than is a standard. But in order to put either equal or not equal, depend. If we know the starting point is here 3, we put equal. And then we don't know the ending point. So once we don't know the ending point, we can't put equal here. without equal. And what is the value here? Because this is and so on, it means infinity. So the complete value, or sorry, the complete formula for this sequential, we can write as an equal to an minus 1 plus 5 for 2 less and equal n yn, because we utilize n variable. If here we put, for example, z, and z, here we put z. And refer to variable that we will use. Less than, without equal, because we don't know the ending point, and because of we don't know the ending point, we put here infinity. This is the complete formula in order to represent this sequential. Okay, if this sequential, we change something, we put something, for example here, we put here 28. Oh, then we know the ending point is 28, because we know the ending point 28. So here we cannot put infinity, because we know the ending point. Here we change, we put equal. So the question is, what is the value we put at this place? The value, once if we know the ending point is 28, so the value we base on the how many element or number involved in this sequential. Here 1, 2, 3, 4, 5, 6. So we put here 6. Okay, class. For recursive formula, can you get the idea? Once you change some value in this sequential, the formula will be changed. So far, okay, class? Ibrahim Hussein? Okay, good. Another person? Anis Zulaika? Okay, thank you. Thank you, others. Okay, good. So this is the idea of recursive formula. So in order to represent the formula for each recursive, we must justify the sequential first. What is the pattern? What is the starting point? What is the ending point? Okay. Now we still talk about recursive formula, but once I give to you and so on, 3, 8, 13, 18, and 23, and we know the ending point 28. So how we adjust the formula for this kind of case? The ending point we know, but the starting point we don't know. So what happened to this recursive formula? So this is a not recursive formula because it not fulfill the idea of a recursive formula. Why? Because the recursive formula must know the starting point. So this is not recursive formula. So bear in mind, or please remember, we must know the starting point. Okay? Okay, now we move to the next idea, explicit formula. Again, recursive formula based on the, in order to find the next term, we must know the previous term. And how we justify the formula and the range based on the pattern of the sequential. Now we focus on explicit formula. Explicit formula, for example, for this case, we have 1, 4, 9, 16, and 25, and so on. So how we produce a formula for this explicit sequential? Okay, again, as previous explanation, I already told you that this one put in A1. The whole sequential we say AN. So for first place, A1, the value at first place is 1, and followed by the value at the second place is A2. So we put A1 equal to 1 square equal to 1, A2 equal to 2 square equal to 4, and so on. So once we look on this pattern, and this pattern actually it refer n. But this one is fixed. This one is fixed too. So we can represent based on this pattern, we can represent that here actually is n. Represent an. So we can represent that the formula is n because 1, 2, and so on until 6. It also follow 1, 2, and so on until 6. So we can represent that n and what? N squared. Because this one is fixed too. So the formula is n squared. So what is the range? The range here, how we produce the range? So formula an equal to n squared. So an equal to n squared for 4. So what is the range? The range is 1. Why 1? Because we only utilize n only, not n negative 2. No, we just utilize only an only. So they have no an negative 1 and so on inside this formula. So we just utilize an equal to n squared for 1. 1 less than n equal because we know the starting point. So that's why less n equal, and less than not equal because here is and so on. So we put, in order to represent and so on, in this case we put as infinity. That's why the formula for this sequential, so finally we put an equal to an for 1 less than and equal n less than infinity. That's the formula for this sequential. That's explicit. Explicit normally here 1. Recursive normally here 2, but depend on the formula here. If in this area we have, for example, an equal to an minus 1 plus an minus 2, so on. We need to calculate how many variable involved. So the total of the variable involved we put here. For this case, 1. Okay. Now we work from opposite side. Given to you the recursive formula. So it say recursive formula, then given to you this formula. Not given to you a sequential, but given to you a recursive formula, and we put this value as a starting point. So we put C1. So C1 means the starting place of the sequential. So the question asks you, please list this sequential. Please list this sequential. So we look on this formula first, this part first. Okay, this part say Cn equals Cn 2 times Cn minus 1. So we can see that starting point is 5. So the starting point is 5. In order to get the second location, we need to utilize this formula. So this formula say in order to get C2, so C2 is 2 times with C1. Why? Because here is n equal to 2, C2, it will be 2 times with C2 minus 1 equals C1. So it will be equal C1. So C1 is 5. So we can get the idea is 2 times 5, the answer will be 10. So here 10. So what is the next? Times 2, 10 times 2, 20. So what is next? Because this pattern times 2, it will be 40. So how many number need in this sequential? We look on this value, 6. So it means we need to list out 6, not more than 6 or less than 6. So here 1, 2, 3, 4. So the next 18. The next 116. So 1, 2, 3, 4, 5, 6. So enough. So this is the answer for based on this formulation in order to represent recursive formula. See, that's why say 5, 10, 20, 14, 18 and 160. Why until 160? Because only 6. If here suddenly we put infinity. So how many we need to list? At least 4. The 4 is standard. So we need to if here we change to infinity, it means the answer will be 5, 10, 20, 14, comma, and so on. If the formula, they have no equal and here infinity. So if like this kind of formula, the answer will be like this one. Okay. Once you change just a little bit value in the formula, the sequential of the representation of sequential will be changed just a little bit. If you put here 4, we just only to represent 5, 10, 20, 40. No need here. And we need to put equal because we know the ending point here. So we put equal. Okay, so far so good. Now we move to example 6. Okay, another idea. What is the recursive formula for above sequential? Based on this kind of sequential, we can see from here to here, here to here, in ascending order, not descending order. So ascending order, in order to represent ascending, we put plus, because increase. Plus what? Plus 4, plus 4, plus 4, plus 4, plus 4. So the starting point is 3. So the formula, now here we utilize D. Previously I said AN. Now once here we put D, so the others also D. Here dn equal to dn minus 1 plus 4. Why plus 4? Here is fixed in fixed order, descending order. Ascending order plus 4. So dn equal to dn minus 1. If here I said en, here must change to en, here also must change to en. What is the variable that you use? We must consistent with that variable. So here for the example, we utilize dn equal to dn minus 1 plus 4 for 2, why 2? Because here dn and dn minus 1. 2 less than or equal to n, less than infinity, because here do not have equal. So d1 equal to 3, refer to the first value. Okay, another example. Okay, example 7. Example 7 given to Sn. So what this? Find the sequential for the given explicit. So once it says explicit formula, you must understand each of the variable focus on the location. Explicit formula. So Sn. So we utilize S. So Sn equal to minus 4. We put a bracket here. We put parentheses. So n, power of n for from 1 less than and equal n less than infinity. It means the ending point and so on. So based on this idea, n, because of explicit, it focus on location. So n1, n2, n3, n4, infinity. So only n4, comma, and so on. So what is the n1? So if an, we put as a1. So here we change to 1. Automatically here also 1. So s1 equal to negative 4 power of 1. It will be negative 4. So the first value is negative 4, as shown here. The second value, if a2, so it will be s2. So S2, if n here 2, here also 2. So it will be negative 4, 2. It will be negative 4 times negative 4, it will be 16. So here, that's why 16. Then come to, if you put as 3. So n equal to 3, here also n equal to 3. So it will be negative 4 times negative 4 times negative 4. It will be negative 64 here. So for the fourth location, n4, it will be 2, 5, 6. And because of here infinity and no equal, so we put and so on. So based on this answer, it will be negative 4, 16, negative 64 to formula for the given sequential. So it means we don't know this is recursive or this is sequential. Luckily, this value actually can represent for both formula, explicit and recursive. How? Okay. Sorry. Now we look on the pattern. We know the starting point, we know the ending point. So we look on recursive first. Recursive from here to here plus 5. From here to here, from here to here, 5. But in descending order, so we need to put negative. From here to here, 5, but negative. From here to here, negative 5. From here to here, also negative 5. So once we look on the pattern, it fulfills for recursive formula. So based on this pattern, we can produce a recursive formula. For example, we utilize d as a variable. So dn equal to dn minus 1. Here, negative 5, negative 5. So negative 5 for what? For there are two variables involved for 2 less than and equal n. Why less than equal n? For we know the starting point. And less than and equal to because we know the ending point. But what is the value here? The value here based on how many number involved. 1, 2, 3, 4, 5. 5. So we put 5 here. So that's the answer or the formula for recursive formula here. And the starting point and d1 equal to 3. So that's the exactly answer. Okay, now we look on, is that fulfilled for explicit formula? Yes. Why? We know the starting point, we know the ending point. This location, we know they have a location here. So we look on what is the previous location we can predict. The previous location we can predict actually, once we look here, 87 actually plus 5, if plus 5 will be 92. Oh, sorry, 92. So based on the previous term here, in order to get the explicit formula, we look on, we still sustain negative 5. But negative 5 of what? Of n. So because from here to here, negative 5 based on the location. For example, here n 1, n 2, n 3, n 4, n 5, here n 0. So because here negative 5 based on the location, so f, for example here, f1. So we put negative 5 and 92, this value. How it comes? Based on the location. For example, in order to find the next value, for example, n1 here, is n1 here, it will be 92, negative 5, because n equal to 1, So for example here D1. So D1 is 97. So D1, because here the first location 1, so 1. So 92 minus 5 times 1, it will be 5, equal to 97. So fulfill 97. And 2 here, and 2. 2. So 92 minus 5 times 2, it will be 92 minus 10. So the answer will be 82. So the value of on second location, it will be 92 here. And so on. See the pattern? So explicit formula quite tricky to get the answer, but if we look on this pattern, we try to guess the N0 value first. Then based on the idea, we look on this pattern. So because of the pattern represent the whole value at that location, so this is the formula. So Dn equal to 92. 92 is N equal N0 minus 5 for each location N. So for what? For 1. Explicit formula normally utilize only one variable. So equal to less than N equal less than 5. Why 5? Because of 5 number involved in this equation. That's the explicit formula for this sequential, and that also can produce an explicit formula for this sequential. So sometimes we can get a recursive on some sequential, but sometimes we can get two formula, a recursive and explicit formula for some sequential. For example, this case. So don't think only one sequential can produce one formula. It can be both recursive and explicit. Okay, that's about pattern, recursive formula and explicit formula. So far, class okay tak? Okay, question for... Okay, yes. Okay, so far okay, class? Okay. Now finish about recursive and explicit formula. Okay, thank you, Hanim. We still talk about sequential. Now we move to the idea behind sequential. How we represent sequential through character, through word, or through sentence. Okay. Now, given to you one sequential, but not in number, in word. For example, here discrete. Finite sequential contain a letter from the ordinary English alphabet. Here the word discrete. How we represent the word discrete? This word discrete in discrete structure. So we need to represent from here. This is one word. One word in computer or in discrete, we represent by this symbol. Once we have this one, how we represent? We need to split each of this word based on the letter. So it says that sequential content of letter. So we focus on letter. Now D, I, S, and so on until E. From here, in discrete, we represent through this sequential. Okay. Then how about string? String means here one sentence. String. How about we represent this string? So Normally we utilize this symbol. In discrete, we need to represent this sentence through word. Like here. Like now is the time for test. So now, comma, is, comma, the, comma, time, comma, for, comma, test, comma. See how the discrete represent. If we look on this one word, it present through letter. If given to you one sentence, we need to represent through word. That's the idea of the discrete. Okay. Another representation. If given to you 1 0 0 1 0 1 0 0 1 1 1, because here they have a repeated value here. Yeah. But one time they have repeated value. In discrete, we only consider either we represent all this value through set. Idea 1 0, we open the bracket here. 1, 0, close the bracket, or 0, 1, open and close the bracket. So if we have this kind of value, we need to represent through set. Either this representation or this representation. Okay, that's if the repeated number. Okay, exercise. Okay, given to you this set of correspondence based on the following sequential. How we represent this sequential? So we just consider the exactly value. Here A, B, B, and so on. So represent only 1A, 1B, 1C, and so on. So the answer will be in discrete. So we convert to discrete. So it will be open the bracket A, comma, B, and so on until Z. Here and so on represent the next value, and the last, the ending, we put as Z. So the second question is 1357. So if we look on 1357, actually all this value is odd number. So we just represent through the this kind of representation. So X represent where X element in Z plus, Y, Z plus. This is a odd number, positive number. Why? Because it start 1, 3, and so on. That's why here positive. If we start here negative, negative 1 or negative 1, negative 3, and so on, here we do not, we can't put positive. But if here we start with negative 1, negative 3, negative 4, and so on, here we change to Z negative. So it represents the whole number of the negative. So Nx is an odd number. Okay. Exercise. Okay, I hope you can do this exercise. The exercise already given the answer, but try to find the way how we get this answer. So write the first four. See the first four. The first four element for the following equation where n equal to 1. So try to get how we get this answer and how this question we get this answer. Try to do the exercise. I don't want to show to you. Try to do it by yourself. Okay. Then it's also for this exercise. Try to do it. This is the answer. And try to study. Try to study this exercise and do the exercise and compare your exercise with your answer with this answer. Okay. Now we move to the next idea. The next idea of sequential. Again, first we talk about formula. Second, we element in the set. So we represent as FFA. Okay, now we utilize FA. We can put FB, FA represent a set. F represent as a function. Means function of set is defined as FA X, where all the element exist in A, we put 1. If do not exist in A, we put 0. This is the standard representation of the set through function. This, once we put 1, 0, 1 represent the existing value in A, 0 represent which the element do not exist in A. These two choice we put as a function. So function means we have the choice exist or do not exist. For example here, this theorem, theorem no need, I think we learned already through maths, where X element in A. So we put okay, here supposedly 1 for 1, 2, where X element in A, here 0 for otherwise. Okay, so given to you, this is universal set. 1, 2, 3, 4, 5, 6. It means the maximum value is 6. The maximum value involved in 6. But for set A, in this universal set, only represent value 1, 2. B, set B represent 2, 4, 6. Set C represent 4, 5, 6. So 4, 5, 6 for C, 2, 4, 6 for B, 1, 2 for A. Now, how we represent through function, where it said that only 1, 2 involved in A. So, in order to represent, we put one set here. How many? 1, 2, 3, 4, 5, 6. So, 1, 2, 3, 4, 5, 6. It means there are 6 locations. Represent 1, 2, 3, 4, 5, 6. So for A only involve 1, 2. So for A, FA only involve 1, 2. So exit for 1 and 2. Otherwise 0. That's why the answer look like this representation. For B involve 2, 4, 6. So 2, 4, 6, the location of 2, 4, 6, 2, 4, 6. So that's why here 2, 4, 6. So the existing for this location, we put 1, 1, 1. Others 0. Oh, sorry. Okay, how about C? C for F, B, for C, so we can represent 1, 2, 3, 4, 5, 6. So C only consider C only consider C only consider 4, 5, 6. So where it is location 4, 5, 6? Here 4, 5, 6. So we put 1, 1, 1. The otherwise 0. That's the idea of computer representation through this location based on this set. Okay, this one don't need. Okay, how about once it we need to represent the whole. For example, previous idea we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We need to represent the whole unit set. We just put 1, 1, 1, 1, 1, 1. That's the idea for the whole value in order to represent F, U, X, not U, universal. Okay. Okay, now given to you here, A, E, R, sorry, yeah, okay. For this case, example 13, given to you, the universal set is A, B, E, G, H, R, S, W. So, to represent the whole element in this set, how many elements involved? 1, 2, 3, 4, 5, 6, 7, 8. So here we put 1 byte, we put 1, 2, 3, 4, 5, 6, 7, 8. So we put 1, 1, 1, 1 in order to represent this set. So from 1 to 8. So if A only represent AERW, so the location of AERW, AERW, so it involves location number 1, location number 3, location number 6, and the location number 8. So because of A equal to AERW, so the way we represent this set through function, we can represent through this idea. So FAX for A, where AERW, we put 1 if AERW. So we put 0 if X, the opposite value, where BGHR. So then once we present this function, so we can create this computer representation. Location number 1, location number 3, location number 6, location number 8. So from here we represent through function, then we represent through computer representation. So that's the idea for example 13. Okay, that's it for today for 1.3. Class, anything? So far okay? So in summary, we can say that there are 3 things you have learned in 1.3 sequential. First, what is the sequential through explicit formula and recursive formula. Second, how we represent the number, the letter, the word, and the sentence. And the third thing is what is the representation if we need to represent through computer representation. So in order to represent the element through computer representation, we need to transform to function first. Then from the function, we can identify how we represent the element based on the value 0 and 1 in the 1 byte. Okay, thank you. That's it for today's lesson.